So in this video, I'm going to try to provide a geometric justification for the directional derivative formula. So in the previous video, we developed the directional derivative. That's this guy right here. So we defined the directional derivative. And then the claim that we made is that if we want to calculate the directional derivative in the direction of u hat, we don't actually need to calculate this difference quotient taking the limit as t goes to 0, that there's a shortcut for it. And the shortcut claim is that if we take the partial derivative with respect to x, evaluate it at whatever x naught, y naught we want, and multiply it by u sub 1, and then we add to that the partial derivative with respect to y, evaluate it at the point of interest, times u sub 2, that this formula will give us the directional derivative without having to go through the process of evaluating the difference quotient. So what we want to do is try to get a geometric sense for why this formula might be valid. So remember, u hat was just the unit vector in the direction in which you're interested in finding the derivative. And we defined u hat to be u sub 1, u sub 2, so it has x and y components. And then we identified in the previous video that if we know the angle theta that u hat makes with the positive x-axis, it's also going to be cosine theta, sine theta. So this is our u hat. So if I establish an x and a y-axis, and then here at the origin, I put my u hat into play. So here's u hat right here. Let's say this is u hat. He's not any specific angle. And u hat, there will be a line that contains u hat. If we put u hat at the origin, there will be a line through the origin containing u hat, or a line parallel to u hat. And we know that u hat makes the angle theta with respect to the positive x-axis. So we've already identified that when we calculate the directional derivative f sub x at a specific value x naught, y naught, that this gives us the derivative or the rate of change in the direction of x. So this is just a number. This is just a number, and it can be plotted on the x-axis, and it would make sense to plot it on the x-axis because it's the rate of change in the direction of x. So I could actually plot, let's change the ink color now, if I can remember how to do that. Go down to ink color and let's grab black. So if we calculate the partial derivative with respect to x, there's going to be a number on the x-axis that corresponds to it. And this could be a negative number as well, but the proof would run the same way, or the geometric justification is going to run the same way, whether f sub x is positive or negative. So kind of without loss of generality, we'll just look at the case where the partial derivative with respect to x is positive. And so this is just a length. And then this vector is u hat, and here's the line that contains u hat. And let's drop the perpendicular from the partial derivative value with respect to x. Drop that altitude down to this line through u hat. So if we drop this guy right here, drop this perpendicular, what I want to notice is that the component of the partial derivative that's in the direction of u hat is just going to be this distance right here. Right? I can decompose the value partial with respect to x into a component that is parallel to u hat and a component that's perpendicular to u hat. And this is something we've actually already done just a couple weeks ago when we were working with vector values. And so what I want to recognize is the partial derivative with respect to x is the hypotenuse of this triangle. This is the side adjacent theta. So this black distance right here is just going to be the partial derivative with respect to x times the cosine of theta by trigonometry, right? this side over the hypotenuse equals the cosine of theta. Multiply the hypotenuse length on both sides, and we get this length here. The side adjacent is just the hypotenuse length times the cosine of theta. So really, this calculation, partial derivative with respect to x times the cosine of theta, is the component of the derivative in the direction of x that is also in the direction of u hat. And then we can do the same thing with the partial derivative with respect to y. It's just going to be some value that we could plot out on the y-axis. It makes sense to plot this number on the y-axis because this is the rate of change in the direction of y. But notice we can again drop the perpendicular down to the line formed by the vector u hat. Drop that perpendicular, and this black line right here is going to be the component of the derivative in the direction of y that is parallel or contributing to the derivative in the direction of our vector u hat. And so the question is, how could we calculate this length? Well, the x and the y-axes hit each other at a 90-degree angle. So this angle right here, the measure of this angle has to be 90 minus theta, right? The sum of these two angles will be 90, so 90 minus theta will be what's left. This is a 90-degree angle here, which makes this angle here have to be theta. And now I notice that this length right here is just the side opposite theta, which tells me that this length is going to be partial derivative with respect to y times the sine of theta. So what we wind up with is the derivative, the partial derivative with respect to x, a component of it is in the direction of u hat, and the partial derivative with respect to y, a component of it is in the direction of u hat. And so each of the partials contribute to the rate of change in the direction of u hat, and we have to take the sum of the change contributed by the derivative in the x direction plus the rate of change contributed by f sub y in the y direction. We take the sum of those to get the total derivative in the direction of u hat. So that's a geometric justification for this formula. Take partial with respect to x and multiply it by u sub 1 because u sub 1 is the cosine of theta, plus take the partial with respect to y times u sub 2 because u sub 2 is the sine of theta. So we can replace cosine of theta with u sub 1 and sine theta with u sub 2 because of how we defined u hat.